Good evening and welcome. I'd like to start by acknowledging the traditional owners of the lands on which I'm joining you from today, the Ngunnawal people. The Academy acknowledges and pays respects to the traditional owners and the elders, past and present, of all the lands on which we operate, live and work. They hold the memories, traditions, cultures and hopes of Aboriginal and Torres Strait Islander peoples of Australia. My name is Paul Richards from the Australian Academy of Science, and I'm thrilled to be here today for a special event as part of Science at the Shine Dome 2021. Traditionally, Science at the Shine Dome is a three-day event in May, where Australia's most influential scientists gather here at the Shine Dome in Canberra. This year, however, things look a little bit different, but in some ways even better, because we're enabling participation across Australia and around the world. So if you're joining us from near or afar, and this is the first time you've been able to participate in Science at the Shine Dome, welcome. You're in for a treat. Throughout the year, we'll be bringing you events online to celebrate excellence in Australian science, recognise outstanding achievements, and to cover important science topics. We hope you'll join us throughout 2021. To launch Science at the Shine Dome, we're here today for our first event. May 12th is the International Day for Women in Mathematics. This day is specially chosen as we celebrate the inaugural recipient of the Academy's Ruby Payne-Scott Medal, Emeritus Professor Cheryl Prager. I'd like to make mention of our event partners, 11 of whom have made this 2021 event series possible. The Australian Government Department of Defence and CSIRO are our Platinum event partners, both of whom have contributed the highest level of support. We acknowledge the ongoing difficult position many organisations are in, particularly in the university sector. On behalf of the Academy, thank you to all our partners for your commitment to excellence. We'll make mention of all Academy event partners as we move through 2021. Your contribution, big or small, enables the Academy to continue to remain independent, foster and champion excellence, and make science available to everyone. Shortly, we'll hear from Professor Prager as she reflects on her life's work and what this medal means to her. And if you have a question for Professor Prager, please enter it in the Q&A section on the right-hand side of the portal. Now, please welcome the Academy's Vice President and Secretary for Biological Sciences, Professor Helene Marsh.
Thank you, Paul. I'm delighted to be here today to celebrate the inaugural Ruby Payne-Scott Medalist Lecture. Unfortunately, I can't be in Canberra at the Shine Dome, but I can't wait to be there soon to see its recent restoration. Work has recently finished to restore the building following hail damage early last year, so its new copper is shining brightly as it did back in 1959 when it first opened its doors. On behalf of the Fellows of the Australian Academy of Science, I'd like to congratulate the recipients of all the Academy Awards this year, especially today's speaker, Emeritus Professor Cheryl Prager, the first recipient of the Ruby Payne-Scott Medal. This medal is awarded to women in science and recognises researchers of the highest standing in the physical or biological sciences. Along with the Macfarlane Burnett and Matthew Flinders medals, it's one of the most prestigious career awards of the Academy and honours Ruby Payne-Scott's seminal contribution to radiophysics and radioastronomy. As Cheryl will explain in her lecture, as a pioneering woman scientist, Ruby Payne-Scott had to overcome significant barriers to help establish the field of radioastronomy. I'd like to make special mention of Ruby Payne-Scott's family, who join us for the event today. Her daughter, Fiona Hall, and daughter-in-law, Jeannie Hall, wife of the distinguished mathematician, the late Peter Hall, a former vice president of this academy. Both Fiona and Jeannie have been part of the Ruby Payne-Scott Medal's journey since 2019. Thank you both for your contributions. Professor Prager has been awarded this medal for her career in mathematics, Before I hand over to Cheryl, I'll read her official citation. Professor Cheryl Prager's work on the mathematics of symmetry has been in the vanguard of a mathematical revolution caused by the classification of the finite simple groups, the atoms of symmetry from which all finite groups are built. She's elucidated the internal structure of these simple groups and driven research on applying their immensely powerful classification to study symmetric structures. Professor Prager developed a theory of quasi-primitive groups, which via her innovative normal quotient method established a new paradigm for working with symmetric graphs and exploiting the simple group classification. Professor Prager demonstrates an extraordinary ability to foster and inspire others, supporting women, advocating for mathematics in schools, and promoting mathematics in emerging economies. It's my great pleasure to introduce Emeritus Professor Cheryl Prager to deliver the Ruby Payne-Scott Lecture for 2021. Over to you, Cheryl.
Thank you, everybody, for attending my lecture. I'm speaking on the lands of the Whadjuk people of the Noongar Nation at the University of Western Australia, and I pay my respects to their elders past, present and emerging. And in this very special lecture, I also want to acknowledge Ruby Payne-Scott, the first woman radio astronomer. I feel enormous gratitude to Ruby Payne-Scott, both for her scientific achievements and also as a trailblazer for women in STEM. What I want to do in this lecture is to tell a little of my story as a woman in STEM and also explain a bit about my mathematics and mathematics of symmetry. I grew up in various country towns in southeast Queensland. I was born in Toowoomba, moved to Warwick when I was 2 years old, and then to Redcliffe on the Moreton Bay when I was 5 years old. And then when I was about 10, we moved up the coast to Nambour. And the reason that we moved so often was that my father worked for the Commercial Bank of Australia. And then when I was about 14, he decided to leave the bank. He became a chiropractor, and the whole family moved to Brisbane, where I finished the last 3 years of my high school. I'd like to sort of put in perspective what was happening with Ruby Payne-Scott and with me for those few years. So here's a fragment of timeline of Ruby Payne-Scott. In 1941, Ruby Payne-Scott joined the radiophysics laboratory of the CSIR, the precursor of the Commonwealth Research Organisation, CSIRO. A few years later, 1944, Ruby performed her first radio astronomy experiment, and in that same year, she married William Hall, Bill Hall. And then 7 years later, 1951, she was forced to resign from what was then CSIRO because there was no maternity leave provisions for her. And several months after she resigned in November, she gave birth to her first child, Peter Hall, who was one of my former colleagues, a very eminent mathematical statistician in Australia. Ruby Payne-Scott's last experience as a radio astronomer was at an international conference at the University of Sydney in 1952. And later in her life, because she really was a very mathematical radio astronomer, later in her life she became an exceedingly good mathematics teacher. So Australia owes a lot to Ruby Payne-Scott. If we look to see what I was doing at that time, 1948, I was born in Toowoomba, and then in 1954, after we moved to Moreton Bay, I began primary school at Humpybong State School on Moreton Bay in Redcliffe. Here's a picture that I found of that international conference at the University of Sydney. It was the General Assembly of the International Scientific Radio Union. It was a very big conference, 500 or 600 people. And in this photograph, we've got most of the radio astronomers who were present at the conference. And if you have a look at that photograph, the only woman is Ruby Payne-Scott. And when I look at that, I think, yes, I was the only girl in my mathematics classes at second year, at third year, at fourth year at the University of Queensland. But that was really a slightly different situation than Ruby had to face. Now let me say a little bit about my mathematics. I am passionate about the mathematics of symmetry. And the same fundamental mathematical symmetry turns up in a lot of different situations, a lot of different contexts. We have the same spiral symmetry in the small fragment of a shell on the beach. The same sort of symmetry occurs in plants, and we might see the same symmetry in a spiral galaxy in the night sky. In mathematics, we study this kind of symmetry and we measure it using groups. And my doctoral thesis in Oxford was concerned with groups acting on various objects, permutation groups, technically the basic ones, the primitive ones. So I worked on primitive permutation groups. Now, symmetry imposes amazing restrictions on structures, and that's what really fascinates me. To give an example of a very simple one that we might have seen looking at architectural features, are wall friezes, the sort that we would find around the edges of walls in ancient buildings or more modern ones. And we use symmetry in order to describe the different types of friezes. So this picture that I have here has some translational symmetries which map the pattern to itself as we move along. It has some reflections, one through a horizontal axis and several through various vertical axes. And the collection of all those symmetries forms the frieze group. And there are, it's been proved, exactly 7 different frieze groups, and these correspond to exactly 7 different types of wall friezes. Now, the same kind of approach is used in many, many different areas. We use it to classify crystalline structures in chemistry by looking at the crystallographic groups. We use the geometry and the symmetry of the structures to study viruses in biology. We use very regular symmetrical experimental designs to conduct agricultural trials. We organise our data structures on the internet to store and retrieve data by very regular, very symmetrical kinds of tree structures. We use symmetry in the types of codes that we use to add error correction capabilities for communication so that we can send pictures back from space. And we use it also in the encryption systems that we use every day for secure communication between, well, our phones and the bank. When I was trying to describe groups and the structure of groups to some people a couple of years ago, I was talking about taking a great finite group and splitting it into 2 smaller groups. Mathematicians would call them a normal subgroup and a quotient group. And so we would start at the root of this tree structure and we would split into 2 smaller groups. And then each of those we would consider in the same way and split that into 2 smaller groups and go on until we can't do it anymore. Since each of these groups, as we go out, is getting smaller and smaller, it's going to stop somewhere. And where it stops are these leaves on this, what we call composition tree, and where it stops is at the simple groups. These are the building blocks for the finite groups. And so all of the finite groups have a collection of simple groups of building blocks that describe their structure. And they're very important. And in 1980, which was about 7 years after I finished my doctoral thesis in Oxford, it was announced first that the classification of the finite simple groups was complete. It actually wasn't, but no one found any more simple groups, but it was an extraordinary announcement. To quote from a citation for the Abel Prize awarded to two of the main players later on, it was one of the greatest achievements of 20th century mathematics. And a young American mathematician, Ivan Andrews, was trying to explain what these simple groups were to his father, and he made a picture of them. He put them together into a periodic table of finite simple groups, a bit like the atoms of chemistry. So that the simple groups, they do mainly occur in families, just as the atoms occur in families. And so for this table, we see several families. Each of these columns represents an infinite family of simple groups. And almost all of the simple groups fit into these infinite families. There's exactly 26 which do not fit, and they're called the sporadic simple groups. And Ivan represented them just singly down at the bottom. It's a hugely powerful tool, and it landed on the mathematical community in 1980. But how to use it? How to use this finite simple group classification outside group theory, or even within it? In my area of permutation groups, around 1980, the same time, there was introduced a new view of primitive permutation groups. It's now called the Payne-Scott theorem. And the primitive permutation groups, the finite ones, were divided up into several types. There's the affine type, think of translations and rotations of space. There's the almost simple groups themselves. They occur as primitive permutation groups. There's another kind called the diagonal type, a little bit mysterious, but that also involves some simple groups, finite simple groups. And then there's a product construction which can be applied to a diagonal or an almost simple type to form a more complicated primitive type. But these are the primitive groups. And the aim was that using this new way of thinking about primitive groups would allow us to attack problems type by type and make it possible to use information about the finite simple group classification to solve them, hopefully. Now, my first attempt at doing something like this also started in 1980. It was with two former PhD students, DPhil students from Oxford, Peter Cameron and Jan Saxel. And we decided to try to solve one of the important open problems about permutation groups in a combinatorial setting using this approach. The one we chose was the Sims conjecture. Now let's pause for a bit. The timeline for me at this stage, 1980, is that I'm married to John. I have one child, James, aged 18 months. I am on my first sabbatical in Cambridge, which is where I had gone to work with Jan Saxel. Peter Cameron had come across from Oxford to give a seminar, and we were discussing what we might do, and it started off at that point. So what is the Sims conjecture? Charlie Sims published a paper in 1967 when he asked this question or made this conjecture. So we'd known about it a little bit longer than that, so it was about 15 years old. It's to do with graphs. Graphs consist of vertices and edges, and I've drawn some pictures of them on the right-hand side. The vertices are the little red dots and the edges are the black lines joining some of the vertices. The graphs Charlie was interested in were regular. Every red vertex was joined by a black edge to the same number, say k, of other vertices. And for all of the pictures on the right, k is 3. They're all 3-valent graphs. And Charlie wanted his graphs to be very, very nice, very symmetrical. Every vertex is like every other one. Every edge is like every other one. And in particular, or moreover, this group of symmetries of the graph was primitive on vertices. So it was a primitive permutation group. His conjecture was, if you take one of these graphs, you look at the number of symmetries or automorphisms that fix a vertex, move around the rest of the graph. That number of symmetries cannot get too large. It should be bounded above by some quantity depending on k. And in his paper, he solved this conjecture when k is 3, and he proved that this upper bound was 48. You could get as far as 48, but you couldn't get any bigger than it. So he thought there should be a number like this for every value of k. So we started working on it using this new approach with Peter and Jan. We didn't quite know enough about the internal structure of the finite simple groups, so we enlisted the assistance of a US mathematician, Gary Zeitz, who joined us, and our finished paper was published in 1983. So we were successful. It was maybe the first time that this approach had been used for a fairly stubborn open problem about primitive permutation groups. It introduced a completely new methodology for working with graphs and for working with permutation groups. You might call it a new paradigm. For us, it was very exciting, but not everyone had the same point of view as we did. It was somewhat controversial. I remember giving lectures about this at conferences and being confronted with very angry colleagues afterwards. They were not really just angry that their favourite problems had been demolished by introducing this powerful new tool, but they had this feeling that using such a powerful tool as the simple group classification was an inappropriate method. From my point of view, it was good to know what the answer was. We knew we were using very, very powerful tools. We had to acknowledge it. But it did change the world. It changed mathematics, the mathematical world, very much. So, oops, that didn't turn. So what happened next? What else did we do? Well, there was more success. I worked more with Jan Saxel. We studied a family of graphs called the distance transitive graphs, a very important sort of metrically regular family of graphs. And using this method opened up the possibility of classifying these graphs by using the Onan-Scott theorem and working with simple groups and working with their representations. I continued to work on different families of graphs. I looked at ones which were called the S-arc transitive graphs. These were the graphs that underpinned Sims's conjecture. And I studied them from this point of view, and I realised that I could not use the theory about primitive permutation groups. It simply wasn't appropriate. When I tried to do something similar to these S-arc transitive graphs, I arrived at a special family which did not have a primitive permutation group acting, but one from a rather large family of groups called quasi-primitive. Nothing was known about quasi-primitive groups, so I had to set about developing an Onan-Scott theory for the quasi-primitive groups so that we could study these graphs. And at the same time, I introduced a now standard methodology for studying symmetrical graph families, which is called the normal quotient method. And the idea is that you take a graph and you divide up the vertices into smaller parts, and you squash down the parts of the vertex set into single vertices, so you're really getting for yourself a smaller graph. And the trick was to do this while maintaining every bit of symmetry that you were really interested in. So this was this normal quotient method. It was very successful. So what's happening now with the timeline? I talked about 1980 with the announcement of the finite simple group classification and the beginning of the work on the Sims conjecture. The work on quasi-primitive groups wasn't published until 1992, about 12 years later. And in between, in 1983, I was appointed Professor of Mathematics at the University of Western Australia, still married by this stage with 2 sons. And there are two things that I'd particularly like to cover as well in the lecture, which happened along the way. Let me show you what happened with my appointment as professor. It was quite newsworthy. There were plenty of coverage in the newspapers, usually on the women's pages, and there were photographs of me and my 2 children. Timothy, aged 18 months, and James, aged 4.5. There was also a photograph a few months after my appointment which involved the four of us, John and myself and the two boys on a tricycle. But by the time it was published on the front page of the West Australian, they'd sliced John out of the picture, and they just had the three of us down the front there. So there's some interesting media interest in these sorts of events. But for me, I felt like I had dual responsibility. I felt I had this responsibility to maintain my research at the forefront in permutation groups and in understanding more about the finite simple groups. But I also felt a responsibility as professor to ensure that the teaching of mathematics remained at the cutting edge, reflecting new developments in mathematics. At the time, digital computers were just beginning to be used in group theory as they were in every other area of mathematics. But our curriculum in pure mathematics at UWA wasn't really at this cutting edge. It was lagging behind some of the other universities, say in Sydney. And I knew I needed to develop a new research interest which would involve computation and groups in order to keep the drive of making sure that we were going to update the pure mathematics curriculum. So I want to talk about each of these two areas. So the first one, being up to date in my research. I felt like everything was happening overseas, and with two little children it was difficult to keep up with everything and to go overseas. And in 1985 I did travel to Cambridge on a 6-week research visit funded by the UK Science Research Council. It was a turning point in my career. 1985, my children are aged just 6 and not quite 3. So how on earth was that possible? Well, I had a huge support from my husband John, and also my mother Queenie and John's mother Marjorie came to Perth for 3 weeks each to help care for their grandchildren. Mathematically, the outcome was very important for me. It was a very important classification of maximal factorizations of the almost simple groups with my two colleagues, Martin Liebeck and Jan Saxel, with whom I worked. It has many, many citations. It continues to have dozens of citations every year, so it's an important work. The other side, the computation. For me to be involved there, I needed to become familiar with the area, and I'm very grateful to a colleague, John Cannon, from the University of Sydney, who was extremely generous both with his time and his expertise. John Cannon is the author of the International Computer Algebra System MAGMA, and at the time it was the precursor of MAGMA, Cayley, that we were talking about. John helped us to learn about it, and I had a very steep learning curve about the basic algorithms, the data structures, the complexity. And John would flick unsolved problems over to me to solve. Eventually, there was a small research project. Eventually, with John's help, I developed curricula, and I taught a new honours course on algorithms for group computation here at UWA a few times. But the watershed for me was an invitation to a specialist international conference in Germany. At that conference, Joachim Neubuser, who is the author of the other International Computer Algebra System, GAP, asked a question. He said, there are no efficient algorithms available for computing with groups of matrices acting on finite spaces. There are very efficient ones to compute with permutation groups, but not for matrices. Surely, Herr Neubuser says, surely someone can give an efficient, maybe randomized algorithm to recognize if a given small set of matrices will generate, if you multiply them together, will generate all of the determinant 1 matrices at least, the special linear group. Listening to this after dinner conversation was me, and there was my former DPhil supervisor Peter Neumann. We both jumped at this with various different ideas, and we worked together and eventually produced the Neumann-Prager recognition algorithm for special linear groups. It relied very heavily on the finite simple group classification. It was published in 1992, so all of these works take several years to finish. It is super fast because it relies on the simple group classification instead of making a lot of time-consuming computations. And it also launched the Matrix Group Recognition Project, a computer project involving dozens of mathematicians internationally, and now there are computer packages for matrix group computation within both MAGMA and GAP. So these days, there are really two prongs of my research. I am still very, very much involved in working with symmetrical structures, graphs, designs, geometries. I produce new theory, new methods to work out how to exploit the finite simple group classification in these areas. I'm also, of course, involved with working out the new theory about simple groups that we need to solve these problems. On the other hand, I work with algorithms for computing with groups. It involves a lot of randomization, a lot of statistical estimates have to be done on simple groups, and the idea, of course, there is to use the finite simple group classification to make super fast algorithms for computers. So that's the end of my lecture, and I'd like, before ending, to say again my heartfelt thanks to Ruby Payne-Scott. Ruby was not able to continue with her scientific career past 1951, although she fought hard against having to accept to resign from her position. But later on, this was successful, and I'm one of those beneficiaries, and some of us here are. We had the opportunity of a scientific career, and thank you to Ruby, and thank you to all of you for attending the lecture.
Now, it is my pleasure to welcome live with us today from Perth, Emeritus Professor Cheryl Prager. Thank you for joining us, Cheryl, and congratulations again on this award.
Thank you very much, Paul. I'm delighted to have this privilege of being the first winner of the Ruby Payne-Scott Medal, and I'm delighted to be here this evening. And well, it's wonderful that we can reach everybody. Unfortunately, we're not face-to-face, but well, it's fantastic that the Academy has supported us to have this time together.
Yeah, wonderful. Thank you, Cheryl. Now, you spoke in your presentation about the parallels between your career and Ruby Payne-Scott's. When did you first become aware of her career, and what kind of inspiration did it provide?
I don't think I knew very much about Ruby until about 5 or 6 years ago. I think it was perhaps listening to Brian Schmidt giving a talk at a Science at the Shine Dome lecture, where I heard from him about Ruby, and then I looked her up on Wikipedia, I suppose. So it's such a shame that such a wonderful and important scientist was not better known in Australia for all those years. I hope that we can do something to rectify it now.
Yes, and I think through this award and these kinds of events, great to draw more attention to Ruby Payne-Scott and all the amazing women mathematicians in Australia and around the world. Cheryl, you also spoke in your lecture about similar experiences during university, being the only woman studying mathematics in your classes. Has gender diversity improved much since then in your field?
Oh, I think it's much, much easier. There are many more girls who take mathematics courses, and when I became professor in 1983, I was only the second woman in Australia to be a professor of mathematics at an Australian university. Now we have dozens, 30, 40 of it, although only 10% of maths professors at Australian universities are women. So we've still got a long way to go, but it is much better than it was.
Now, you chose to give your lecture today, which is International Women in Mathematics Day, marking the birthday of groundbreaking mathematician Mariam Mirzakhani. If there was a young Mariam watching today, what would you say to her?
Oh, I'd say if you really want to do mathematics, just grasp every opportunity you can and go for it. I mean, don't listen to people trying to put you off. I think for anybody in any area of endeavour, it's wonderful to just meet those challenges and try your best and just go all straight out for it.
You certainly did that in your career as well. I'd like to ask you a little bit more about your own research and discoveries now. Now, the kind of fundamental science that you conduct, as you mentioned, has a wide range of applications. You gave a few examples, but one in particular stood out to me. You said, we use symmetry to study viruses in biology. How important is the role of fundamental research in applied science, like responding to the COVID-19 pandemic?
Well, fundamental research can never be guaranteed to be effective, but I very recently listened to a wonderful colleague of mine in the UK who does work exactly on that, on the symmetries of viruses, and she is most definitely contributing to trying to understand how viruses replicate and how they could be perhaps encouraged not to. And she is doing work in exactly that area. But there's so many different areas where the same kinds of fundamental mathematics help us to understand exactly what's going on. And I guess that's what mathematics does. It extracts the essence of a problem, and then the theory that we develop hopefully is ready, poised to be applied in many, many different areas. As we're seeing in the statisticians working in trying to understand the way the pandemic is moving around the world.
Now, listening to your work on the Sims conjecture was just fascinating. It took 3 years from beginning to work on the problem until your paper was published, which is an enormous effort. What was it like to apply finite simple group classification to this kind of problem for the first time?
We couldn't be confident that we would be successful. We had the new tool, well, two tools, the simple group classification and the Payne-Scott theorem. We knew we could make progress and reduce everything down to a really tough problem about simple groups. And then we knew that there are certain aspects of the simple groups we needed to know about, and at that time we didn't know about. So what we're finding is that every new challenge is telling us that we need to know more about the fundamental aspects or the fundamental objects. So we were just lucky to know about the appropriate person with the appropriate expertise to answer the one question we needed answering. And once we had that done, we just felt so elated that we'd really got the problem solved.
Yeah, it was, simply an amazing discovery and obviously having implications now as we continue to learn more. And you described another turning point in your career when you were able to travel to Cambridge. And there you were able to achieve classification of maximal factorizations, I hope I said that right, of the almost simple groups. And as you said, it continues to have dozens of citations each year. Now, the question I wanted to ask you is, how valuable was the support you received at home, but also the opportunity to travel overseas for this work?
For me, it was a game changer. I felt that everything was happening on the other side of the world, and with young children and huge teaching responsibilities, I was not getting the chance to really talk with the people who were doing this work. And it was very interesting. I had been working with my two colleagues fairly regularly, every couple of years. They were coming to visit me in Perth. I was getting grants to bring them here. But I really needed to get overseas and work with them and have the opportunity of going to some international conferences while I was there. And having that really intense time, I think we worked out in the 6 weeks exactly what needed to be done and how we were going to be able to do it. And then it took another 4 years to get all of the details correctly done. I mean, it was a huge undertaking, but it was worthwhile because it's been so useful in just everything that you're doing. My newest PhD student is using that work in the project that he's started to work on this year.
That's absolutely astounding and wonderful. And I hope as time goes on, as you see that your work continue to be cited and see it applied in an ongoing basis, that must be very gratifying to sort of see the lasting impact of all the effort that you put in those years ago. The other big area of your research, as you mentioned, is digital computation. And the Newman-Prager algorithm was published in 1992. How is the field continuing to develop all these years later?
Well, that algorithm opened up a huge international project to get a really complete collection of methods and algorithms to work with groups of matrices. And that's just about coming to a stage where we can solve most problems. There's still some that we need to do better and a couple that we don't quite know how to do, but we've got proper computer systems to answer almost every question we want to ask about groups of matrices on finite fields. It just leads us to the other areas that we can't solve, but I mean, we've got very, very powerful computer systems that are just so much more powerful than they used to be now that we're incorporating the simple group classification into justifying the algorithms.
Well, Cheryl, I'd like to get to a couple of audience questions who've been tuning in and listening in tonight. The first one is that's been sent in is, if simple groups are like elements and the classification of finite simple groups is like the periodic table, then are primitive permutation groups like molecules? And if so, is this analogy helpful?
Oh, that's such a neat question. So primitive permutation groups are ones where we try to break them down into smaller and smaller bits, some basic ones, just the way we tried to break the groups into simple groups. And you never quite get them down to being simple. The Payne-Scott theory was telling us what the basic building blocks were going to be like. And I guess they really are like molecules. They're like simple groups all fitted together in a particular way. And there's still just these important types of, I guess, of the molecules that we use to study groups in action. That's a really nice question.
Now, I've had another question sent in just through our on-air chat. Now, the question is, as you noticed, Ruby was the only female in the radio astronomy group led by Joe Pawsey. This person asks, she was a mathematical specialist. Are women better at mathematics? I don't know if you can answer that, but that was the question that's been posed.
I think people are good at mathematics, boys and girls, men and women. What I do think is that if we ignored half the population because of some way of dividing them up into two, then it's a waste of talent. There are some extraordinary women mathematicians, and as you mentioned, Mariam Mirzakhani, the only woman to win a Fields Medal, she is one of them.
Well, just my final question for tonight, Cheryl. You've held your position as Professor at the University of Western Australia now for around 40 years. How does the fact that Ruby Payne-Scott wasn't able to continue her career beyond 1951 continue to motivate you today?
I feel such gratitude to people like Ruby Payne-Scott who really fought very hard to be able to continue as scientists. And I met some other women when I first arrived as a junior lecturer who were, again, able to continue but not have permanent positions. So I think we're very, very much fortunate in our personal lives to be able to have a scientific career and a family. And also Ruby's amazing intellect through her work for radio astronomy is something that we can all try to emulate. And I don't know, I think I understand a little the drive that she has, because I just remain passionate about trying to solve the difficult problems.
Yeah, that's very clear, the passion that you have. Cheryl, thank you so much for speaking with me tonight. It's been an absolute honour, and congratulations once again.
Thank you, Paul. Thank you.
Well, that is all we have time for tonight. I'd like to thank everyone across the globe who has joined us to celebrate science. Thank you again to all our Science at the Shine Dome 2021 event partners. Our next Science at the Shine Dome event will be on Wednesday, the 28th of July, the Matthew Flinders Lecture for 2021, presented by Professor Andrew Holmes. We hope you'll join us then. Once again, thank you and congratulations to Professor Cheryl Prager. I'm Paul Richards. Have a good night.